So this will work like this. So we have 3 hands-on sessions. In all hands-on sessions, I will tell you a bit more about the theory behind, and then we'll move to a live demonstrations of how to do this, what I've shown you. And then there will be a really practical part in which you will be actively doing the analysis after I divide you into breakout rooms. So you will just be you will be able to follow the step-by-step tutorial that you can download here and here on Indico, and you will try to do these things yourselves. Assuming you were able to download MATLAB and SPM, I hope that's the case. Okay. Okay, and I heard that some people were having troubles with getting SPM working on Mac, and unfortunately, I heard that there are issues with Mac, the new Mac that use an M1 chip and SPM that is not compatible yet. So in your case, please just follow. And we will, and yeah, I mean, you need to use another computer for now, unless there's been some updates, but I'm not aware of them. So let's try to okay, let's try to move on. So preprocessing. So basically, here we're talking about quantitative analysis in SPM. SPM is just one of the many softwares that you can use to do this kind of things, of statistical comparisons. It's one of the most commonly used. Other are, for example, FSL. It's really a matter of arbitrary choice. For clinical applications, I think SPM is kind of the most commonly used to derive as a single subject maps of alterations in patients with disorders of consciousness in these cases, but there has been also applications in case of dementia. So how does it work? What we want to do is to run a voxel-wise analysis in which we compare our patient to the healthy controls. Here to the healthy controls. To do so, the first step is very simple, is really to put the patient in the same space as the healthy controls, because every image is different. Our brains are different, and they are in a space which is called native space, which is different from the space of the healthy controls that we want to use for comparison. So the first steps are really about, you will see later, is really about try to put the patient image in a space that is the same as the healthy controls images. So if you open an image of the patients, and you will see it later, you will see that even if you open 2 different images, each image will be in a specific space called native space. So if I open 2 images at the same time and put the same coordinates, I will get 2 different points. This is again because these are images in native space. So each image is showing is reflecting the space of the patient, and this space is not comparable. So what we need to do as a first step is to register the image of the patient, and we can do this in SPM, and I will show you how. As a first step, we really just want to do something very rough, putting the image of the patient, trying to align it to the image of our healthy controls, let's say. And we do this, and we can do this using rigid transformations, like rotations and translations. So we are just moving the brain with a rigid transformation, so we are moving each voxel in the brain in the same way, either rotating it or translating it. And we can do it in SPM using these functions. We use a display function, and when display window comes up, we can use pitch, roll, and yaw to rotate our brain of the patient, and trying to put it from, usually again the patient brain is kind of rotated because the patient is not always perfectly aligned to the PET scan, so it can be a bit rotated to the left, to the right, up or down, all across the 3 planes. And we really want to put the patient's brain from here to here. So we want to have a brain that is quite as let's say as horizontal, as aligned as possible to the 3 planes. And I will show you how to do this, but this is the first step. So here we are just really trying to reorient, let's say, the patient's image to a more or less standard space. But this is something very rough, and we just do it because we want to help SPM do the real stuff. So after we do this, the output image is given to SPM for the normalization. So the normalization is the real thing. With the normalization, we really take the patient image and we transform it into the standard space. And for standard space, I mean, in our case, the MNI space, Montreal Neurological Institute space. This is just a standard space that was computed based on a large sets of images, and is the most commonly used right now. So this is a standard space. If we put our image in this space, our image will become comparable to all other images that are also in this space. To do this, we need 2 ingredients. The first ingredient is a template, which is essentially just an average image of healthy controls or healthy controls and patients. So in our case, for disorders of consciousness, we use a custom FDG template, which was derived from averaging images of healthy controls and patients. Why do we use also patients in the creation of our template? You can also create your template, of course. The thing is, what intuitively one would say, if so the template, what is it? Sorry. The template is the reference image that we use to move our patient image into standard space. So it's really our reference standard. We want our patient image to look exactly as our template as much as possible. Why do we, so intuitively a template should be made of healthy controls, but the thing is, it doesn't work very well when we work with patients that have highly deformed brains. So we have a template that is made of healthy controls and patients with disorders of consciousness, because the normalization works better like this. So we are able to put our patient to standard space better if we use a template that is made of healthy controls and patients. And this is something that is commonly done. So even if you go and look, for example, at FDG-PET applications in the field of dementia, you also have templates that are made of healthy controls and patients with dementia. So you really have to have a template that is of course, specific for your tracer, FDG-PET, and possibly specific for your population. And this template, you have it. It is available inside the coffee break code that you could download from my email of yesterday. So you have these templates, and then we have to transform our patient image to look as much as possible as this template. And SPM does this automatically using a series of affine and linear transformations, which, I mean, very easily, they're just basically the linear transformation. So we have a function that is applied to our image, and all the voxels in our image gets either translated, rotated, zoomed, or sheared in the same way. So it's the same transformation applied to whole our image. But this transformation usually is not enough to really have our image as similar as possible as the template. So there is a second step that involves nonlinear transformations, in which deformations are applied based on it's kind of complicated, but it's really are applied based on these on a field that is defined at the voxel level. So we can transform our voxel in a certain way to really try to match our image to the template. But this is done automatically by SPM. So we have registered our image manually, kind of roughly. Then SPM does the normalization, making our image as similar as possible to a template. And then and here you see what happens. So we start from a patient image that looks like that. This is native space, this is patient space, and then we move it into standard space. And this is how it looks. So it looks much more similar to our reference template. Then, so now if we look at the same coordinates in the same image, in 2 different images, sorry, we will get the same thing. So here we have the right caudate nucleus in both images, but you can see that the images are not perfectly comparable. So to try to improve comparability so that we can really compare them voxel by voxel, we can do something else, which is called smoothing. So smoothing is just applying a blurring filter to the images. We use a Gaussian smoothing, this one that you see on the right. So basically, before applying the filter, this is an example of what we have, just points. After we apply the smoothing kernel, we see that basically our signal gets spread out based on a Gaussian function. Why do we do this? Well, this is done for 3 reasons. Doing this, we can improve the signal-to-noise ratio of the images. We can minimize the differences between our image and the template and any other image we will want to compare. And we also increase the validity of the statistics that we will apply because our errors will be more normally distributed because we are using a Gaussian filter. So, I mean, this is a filter that we would use. And when we do this, and the filter is a Gaussian filter and is defined by a properties that is its width at full width half maximum. So when we go half in the Gaussian, this is defines essentially how much smoothed we want our images to be. If we choose a filter that has a very low full width of maximum, at half maximum, we will have the smoothing effect will be smaller. If we increase the full width at half maximum, we will have a stronger smoothing effect. So we will see a higher change in the image. And here it is what happens. So these on the left are the images before smoothing. Then we applying smoothing, and this is what we get. You can see that we lose somehow a bit of spatial specificity. So the images are not as precise as they used to be before, but they are more comparable between each other. So basically, this is a choice with a trade-off between how much we want to retain spatial information and how much we want to have images that are comparable. And this is very important with our patients because we have highly deformed brains and we cannot compare our patient brains to other images if we don't make it similar. So smoothing is really necessary when we work with our kind of patients. And this is all for the theoretical part. Are there any questions so far about this? Otherwise, if there are, please speak now. Okay, I will show you. You can also interrupt me with your mic, so you can not write in the chat, but really just talk to me if you prefer. And I will just change my screen to screen 1. Okay, so now you should be able to see MATLAB. So for this part, I will use the materials that I sent yesterday. And basically, we have our images. We will use the patient images. So you can go here. And then here, this is what you should have downloaded from the eBrains patients. And then you can choose, I don't know, FDG-PET patient 1. So we will start again from the DICOMs and really show you every step until we get to the register, normalize, and smoothed images. And everything I will show you is also available in the materials that are on Indico here. So you have everything also here. And this is the batch that I will use soon. And you'll see in a second. So first of all, so we have our image here. So this is patient 1 or David Bowie with all the DICOMs file. So first of all, we want to call SPM. So we write SPM-PET. We already put SPM in my path. I call SPM-PET. And for simplicity, I also define my current folder as the folder containing all the DICOM images, and this will allow me to be fast when I have to select things in SPM. So first of all, and Claire already showed this, I click on DICOM import. I select my DICOM files, right click, select all, done. And here I have all my DICOMs. The here SPM asks for an output directory. So where do I want to save my files? I want to save them in my current directory, which I can see here on the top. So the directory that contains the DICOM files. So I'm already where I want to be. I just click here on the dots and I have selected the directory where I want to save my files. Done. And now I just have to click run, and SPM is running the DICOM import, and now it says it is done. So here in my folder, I can see that a new image has appeared. And if you have installed MRI cron, downloaded MRI cron, because actually it doesn't require an installation, you can see here the image of the patients. You can see that it is a bit rotated. So we really need to do the registration, and we do it manually, again using SPM. How to do it? So I am again here. Stop me if there is something, I'm going too fast, there's something that you don't understand, just stop me or write in the chat. What I do is I'm back to my SPM interface. I click on display and I select the image. And you can see here that SPM is very clever. It just shows me the image that I actually need. So the nifty image. And this is why actually we import DICOMs to transform them into a nifty format, because a nifty format is much more usable than the DICOM format, which is every image is a different slice in the brain, and it's complicated to do. So here in this nifty image, I can see the whole brain. So I select my nifty image that I just obtained from the DICOM import. Done. And here, what Claire also showed, I can see the image. Now, what I want to do is I want to work on pitch, roll, and yaw to try and make my brain a bit more straight. So I really want a brain that is as much as possible as oriented on the 3 planes. So I can try a few random parameters. If you use negative values, you are rotating in a counterclockwise way. If you use positive values, you will be rotating in a clockwise way. So here I'm just playing around a bit, and yeah, okay, this is okay. I mean, this doesn't have to be perfect. It's just really to help SPM with the next step of normalization. So here, more or less, the brain is quite horizontal here. Yeah, look, it's okay. Doesn't have to be perfect. So we have rotated the brain to make it a bit more into standard space. The next step is to set the origin. So we want to translate the brain so that the center of the brain, let's say, is corresponds to the coordinates 0, 0, 0 within the image. So we want to change the origin. Here, if we look, the origin of the image, so 0, 0, 0, 0, here coordinates correspond to a point that I can even locate. It's completely outside of the brain. To help SPM run the normalization, we really have to have the 0, 0, 0, this origin point inside the brain. And conventionally, this point is, we want to locate the origin at the level of the anterior commissure, which is, yeah, more or less here. Again, doesn't have to be perfect. It's more or less here. So let's say at the end of the gyrus rectus, in front of the caudate head. But okay, it doesn't have to be perfect. More or less, it has to be here. And once we do this, we want to tell SPM that this has to be consider our origin. So 0, 0, 0 coordinates. And to do that, we just say set origin. And now you can see that the origin 0, 0, 0, 0 corresponds to this point, which is a good enough approximation of the anterior commissure. Doesn't have to be perfect. Now we did this, but we still haven't saved our progresses into into the image. So we just click reorient. We have already selected actually our image that we want to reorient. So translate and rotate based on the parameters that we just selected. So it's already selected. We just click done. Yeah, we can save also this file, it doesn't matter. And now our image, you can see that has been updated to include everything. So to include correctly, you can click origin to have a properly registered image. So this step is done. Next step is to use SPM, and now we will be using a batch. I can close everything to normalize. And to do this, we click on batch here. And now I prepared for you already a batch. So it's, let's say, you will see a module. And the module, I mean, you can download it from Indico. In my case, my module is inside this folder, and I want to upload this batch, normal batch. And this batch contains a series of options that allow me to perform normalization here in the first module and smoothing here in the second module. So what you have to change in this batch are really just 4 things. Actually, sorry, 3 things. It's very quick. So we want to change the source image and be sure to select our registered image of the patient. So in this case, it's this one. Sorry, here there is an image, it's just already selected. I want to deselect it. So I just click on the file that is here, and I want to select my image, and then done. So this is my source image, the image of the patient. I want to modify, to normalize what? Again, I want to modify, again, the image of the patient. So I select it again in images to right. Third things to modify is the template. So I need to tell SPM which template I want to use to normalize. So what is my reference? That is in MNI, standard space, and to which I want to move to transform my image. So I click on template, again, specify. I deselect this one. Now the template, I put it again into, let me find it, sorry, it's a bit here. So into the coffee break script that you have downloaded, you navigate and you have a folder called mask templates healthy controls. And your template is this one, template CTAC 88. This is a template that is made of healthy controls and patients with disorders of consciousness. We select it, we click on it once, and then done. And that's it. We have our batch with smoothing is already selected, and we are using quite a huge smoothing because it's 14. Usually you will see more often 8 in the literature, but here we are really dealing with patients with very deformed brains. So we prefer to have a very large smoothing kernel to really try to make the images as similar as possible to our healthy controls. Why don't you use template from the SPM? If I'm not mistaken, the PET template for SPM, it's a water template. So it's not ideal. So we prefer to use, if you refer to the PET template in SPM, it's a water template, H2O, if I'm not mistaken. So we prefer to use this one, but it's not just a matter of FDG, of the tracer. It's also a matter that this template is made of healthy controls and disorders of consciousness patients, and the normalization simply works better if we use a template that is specific for our patients. So this is the reason. Of course, I mean, we can use different templates. It's a choice of what works well enough. So compared to the SPM standard template, we saw that these templates that we use works better. So we have everything. And my suggestion here is to, now you have modified your batch, ideally. My suggestion is to save the, or you can overwrite it, save the batch with your parameters so that you can always go back. You can load this batch again and check what you did in case something went wrong. So we save the batch, yes, and we run. And now SPM is running the normalization and the smoothing, and it is done. So we have here, you can open it in MRI Cron. There are VU image and SVU image. So S image is our original image that was that we just reoriented manually. Then we have a W image. This image is normalized. You can see that it is a bit different from before. So the image is actually much more similar. I can open it to the template if I can find it. No, I can't find it. But anyway, this image is much more similar to our template compared to as it was before. And here you have also the smoothed image. So you can see after smoothing, this is the final image that we will be using in our analysis. And it's a heavy smoothing that we apply, but again, it's necessary for ensure comparability across images. So this view as image is what we will use for the next step of the statistical comparison with the alpha controls. So that's it.